In chemistry, efflorescence is the migration of a salt to the surface of a porous material, where it forms a coating. The essential process comprises the dissolving of an internally held salt in water, or occasionally in another solvent. The water, with the salt now held in solution, migrates to the surface, then evaporates, leaving a coating of the salt. In what has been described as primary efflorescence, the water is the invader and the salt was already present internally. Some people describe a reverse process, where the salt is originally present externally and is then carried inside in solution, as secondary efflorescence. However, others would give this latter phenomenon another name entirely. Efflorescences can occur in natural and built environments. On porous construction materials it may present a cosmetic outer problem only, but can sometimes indicate internal structural weakness. Examples: a 5 molar concentration aqueous droplet of NaCl will spontaneously crystallize at 45% relative humidity to form an NaCl cube by the mechanism of homogeneous nucleation. The original water is released to the gas phase. Gypsum is a hydrate solid that, in a sufficiently dry environment, will give up its water to the gas phase and form anhydrite. Copper, too, sulfate is a blue crystalline solid that when exposed to air, slowly loses water of crystallization from its surface to form a white layer of anhydrous copper, sulfate. Sodium carbonate decahydrate will lose water when exposed to air. Masonry equals primary efflorescence equals, primary efflorescence is named such, as it typically occurs during the initial cure of a cementitious product. It often occurs on masonry construction, particularly brick, as well as some firestop mortars, when water moving through a wall or other structure, or water being driven out as a result of the heat of hydration as cement stone is being formed, brings salts to the surface that are not commonly bound as part of the cement stone. As the water evaporates, it leaves the salt behind, which forms a white, fluffy deposit, that can normally be brushed off. The resulting white deposits are referred to as efflorescence in this instance. In this context, efflorescence is sometimes referred to as saltpetering. Since primary efflorescence brings out salts that are not ordinarily part of the cement stone, it is not a structural, but, rather, an aesthetic concern. For controlling primary efflorescence, formulations containing liquid fatty acid mixtures have been commonly used. The oily liquid admixture is introduced into the batch mix at an early stage by coating onto the sand particles prior to the introduction of any mix water, so that the oily admixture is distributed uniformly throughout the concrete batch mix. Secondary efflorescence equals, secondary efflorescence is named such as it does not occur as a result of the forming of the cement stone or its accompanying hydration products. Rather, it is usually due to the external influence of concrete poisons, such as chlorides. A very common example of where secondary efflorescence occurs is steel-reinforced concrete bridges as well as parking garages. Saline solutions are formed due to the presence of road salt in the winter. This saline solution is absorbed into the concrete, where it can begin to dissolve cement stone, which is of primary structural importance. Virtual stalactites can be formed in some cases as a result of dissolved cement stone, hanging off cracks in concrete structures. Where this process has taken hold, the structural integrity of a concrete element is at risk. This is a common traffic infrastructure and building maintenance concern. Secondary efflorescence is akin to osteoporosis of the concrete. For controlling secondary efflorescence, admixtures containing aqueous-based calcium stearate dispersion are often added at a later stage of the batching process with the mix water. In a typical batching process, sand is first charged into the mixer, then the oil-based primary anti-efflorescence admixture is added with constant mixing to allow the oil to coat the sand. Then coarse aggregates, colorants, and cement are added, followed by water. If CSD is used, it is then introduced usually at this point during or after the addition of the mix water. CSD is an aqueous dispersion wherein fine solid particles of calcium stearate are suspended in the water uniformly. Commercially available CSD has an average particle size of about 1 to 10 micrometers. The uniform distribution of CSD in the mix may render the resulting concrete masonry unit water repellent, as CSD particles are well distributed in the pores of the unit to interfere with the capillary movement of water. Protecting against efflorescence equals, the only way to completely and permanently prevent efflorescence in cementitious materials is by using special admixtures that chemically react with and bind the salt-based impurities in the concrete when hydrogen is present. The chemical reaction in these special additives fuses the sodium chloride on a nanomolecular level, converting it into non-sodium chemicals and other harmless matter that will not leach out or migrate to the surface. In fact, the nanotechnology in these additives can be up to 100,000 times smaller than even the smallest cement particles, allowing their molecules to literally pass through cement minerals or sand particles and ultimately become part of the cement or sand with which they react. And since they require the presence of hydrogen, they stop reacting as the concrete dries out and begin reacting again when the concrete is exposed to moisture. It is also possible to protect porous building materials, such as brick, tiles, concrete and paving against efflorescence by treating the material with an impregnating, hydrophobic sealer. This is a sealer that repels water and will penetrate deeply enough into the material to keep water and dissolved salts well away from the surface. However, in climates where freezing is a concern, such a sealer may lead to damage from freeze-thaw cycles. And while it will help to protect against efflorescence, it cannot permanently prevent the problem. Efflorescence can often be removed from using phosphoric acid. After application, the acid dilution is neutralized with mild diluted detergent, and then well rinsed with water. However, if the source of the water penetration is not addressed, efflorescence may reappear. Common rebar protective measures include the use of epoxy coating as well as the use of a slight electrical charge, both of which prevent rusting. One may also use stainless steel rebar. Certain cement types are more resistant to chlorides than others. The choice of cement, therefore, can have a large effect upon the concrete's reaction to chlorides. Today's water repellents help create a vapor-permeable barrier. Liquid water, especially from wind-driven rains, will stay out of the brick and masonry. Water vapor from the interior of the building, or from the underside of pavers can escape. This will reduce efflorescence, spalling and scaling that can occur from water being trapped inside the brick's substrate and freezing during cold weather. Years ago, the water repellents trapped moisture in the masonry wall, creating more problems than they solved. Condensation in areas that experienced the four seasons were much more problematic than their counterparts. Image gallery equals. See also, hygroscopy, deliquescent, hydrate. References